Example 12. Write a separate balanced chemical equation for the combustion of each of the following: carbon, hydrogen, and C2H5OH. Consider the only products to be carbon dioxide and/or water. In principle, ethanol can be prepared by the following reaction. Carbon plus hydrogen plus water yields ethanol, or C2H5OH. Calculate the standard enthalpy change for the reaction. Then Part C, calculate the standard entropy change. Part D, calculate the equilibrium constant at 25 degrees Celsius for the reaction. Now write the balanced, separate chemical equation for each of these products combusting. Consider the only products to be carbon dioxide or water. So here's the first one, carbon plus oxygen, we get CO2, and then you make sure that the numbers of the elements on each side are the same. This is hydrogen plus oxygen, makes water. Here we have ethanol plus oxygen, gives carbon dioxide and water. Calculate the standard enthalpy change for this production of ethanol. To find it, use Hess's law. Since we found the combustion equations for carbon, hydrogen, and ethanol, we can combine the equations to find the equation for the formation of ethanol. However, we must keep in mind the number of moles of each compound and multiply the combustion equations to correspond to the overall equation that we're trying to match. Now we're going to look at our different combustion equations. First of all, let's look at the carbon combustion equation. That's right over here. We're going to multiply that by 2. Why? Because we need 2 carbons there in the ethanol preparation reaction. So when we do that, we have to multiply the enthalpy by 2. Now, let's look at the combustion of hydrogen. That's this one over here. Again, we multiply by 2. We need 2 moles of hydrogen. So it's 2 times minus 285.8. And finally, reverse the ethanol reaction, since we need ethanol on the product side. Therefore, multiply its enthalpy by -1. Now, add up the equations and the corresponding enthalpies to get the overall change in enthalpy. So here's our carbon one, here's the hydrogen, and here's the reversed ethanol. So let's see. We have brown, brown, and brown, and those will cancel out. Oxygen goes away. CO2, we have 2 CO2s on the right, 2 CO2s on the left, they go away. We have 3 waters here and 2 waters here, so we still keep 1 water on the left side, and that's what this one is showing. So let me just erase my marks there. And if you'd like, pause and take a look at this and make sure it makes sense to you. And if not, we can keep going. Add up what's left over, and we have 2 carbons, 2 hydrogens, and a water. And on the right side, all we have is the ethanol. Here's the enthalpies we got from the previous slide. Add them together, and we get an overall enthalpy change of 8.1 kilojoules per mole. To find the standard entropy change, we use the absolute entropies in the table and this equation. And that's a little shorter than we normally use, right? Because we normally go like sum of n products times delta S of each product. So this time we're going to assume we've been doing this enough, and we're just going to make sure we put that in our answer. So here's our product. There's 1 mole of ethanol, and that's 160.7. And then minus all the reactants. 2 times 5.7.40, that's carbon. This 2 is hydrogen. All right, so there's hydrogen, carbon, and then there's 1 for water, and that's water. And we get minus 251.8 joules per mole Kelvin. Remember, pay close attention to the coefficients of the reaction species. These numbers, as we just showed you, tell you how many moles of each are used or produced as the reaction progresses and approaches completion. Calculate the equilibrium constant. First, find the Gibbs free energy using this equation right here. And we found delta H, and here's the temperature. And we found delta S. So we carry out the math, we get 83.1 kilojoules per mole. I have this to find the equilibrium constant, e to the minus delta G over RT. Substitute in our values, And notice we need to use joules here because of the universal gas constant is in joules, and we get the equilibrium constant is 2.7 times 10 to the minus 15.